Molecular shape and polarity. We talked about polar bonds. Here's an example of a polar bond. This is a diatomic molecule. It has two atoms. We have a hydrogen bonded to a chlorine. They are not the same, and so I would want you to assume that this is a polar bond. And indeed, chlorine is significantly more electronegative than hydrogen. And so the electrons in this bond are not shared equally. They're going to be spending more time around the chlorine. You can think of chlorine as stealing the blankets from hydrogen, sharing a bed, and the blankets are not shared equally. Or we can think of chlorine as that being a really cool house where these two little boy electrons want to go play. I don't know why it's boys instead of girls. I don't know. And then hydrogen's house is not so exciting, and so they're going to spend more time over here. And this arrow thing represents the net dipole moment. And so this is like, dad's coming up and asking the neighbors, where are the boys? He points, right? Pointing to the more electronegative one that's more attractive to the electrons. They're probably over there. This end is a plus. So this end of the molecule has a partial positive charge, a low electron density. This end has a partial negative charge, a high electron density. So this side got more blankets than the other side, right? More of that blanket. So in a diatomic molecule, if the bond is polar, the molecule's polar. But if we have polyatomic molecules, it gets a little more complicated. It depends on the geometry. So let's look at carbon dioxide. So carbon dioxide has a linear geometry. The oxygens are on opposite sides of the carbon. This is a polar bond with oxygen pulling on the electrons. And this is a polar bond with oxygen pulling on the electrons because oxygen is more electronegative than carbon. And so we can put these little arrow things here representing the dipole moment. So a dipole moment is a vector quantity. It has a direction and a magnitude. If that doesn't make any sense to you, don't worry about it. The direction is going to point to the more electronegative atom. The magnitude, how strong it is going to depend on the electronegativity difference. So with a two-dimensional molecule, we can think about this in terms of playing tug-of-war. Okay. So here we have our rope, and we have one guy over here, one individual, and another individual over here. And then, I don't think they let kids play this anymore in school, but we did this, damaged our shoulders when I was in school. They hang a red flag here, right? And then you're pulling against each other, and you're trying to move that red flag past a certain line, and then you've won, right? So in this situation, oxygen is pulling in one direction. The other oxygen is pulling in the opposite direction. They have the same electronegativity. They are equally strong. So if we have two equally strong people pulling on a rope, what's going to happen? The rope will break. It's a strong rope. Nothing's going to happen, right? They're going to get tired, and eventually they're going to say tie, right? Because they're both equally strong. That flag is not going to move, right? So we can understand this as being vectors of equal magnitude in opposite directions. They add up to 0. So this molecule does not have one end that's more positive or negative than the other. So it's a nonpolar molecule even though it has polar bonds. Everybody okay with that? Let's look at water. So we just learned why water has a bent structure, okay, because it has two lone pairs. The lone pairs are not considered at all in terms of polarity, but the lone pairs are important because they determine the geometry. So here we have two polar bonds. Oxygen's more electronegative than hydrogen. And so both of these bonds are pointing, or the vectors are pointing towards the oxygen. So if we think of this in terms of people playing tug-of-war, so now we've got this one person up here, and got a rope over here and a rope over there, and then little guys down here. Like maybe this is Dad playing tug-of-war at the same time with his twin sons or daughters. All right, let's put a flag in there. What's going to happen? Dad's going to back up and pull both of those kids with him, right? So adding these vectors, there's a vector here and a vector here. Adding those vectors will get us overall a vector like that. So the sum of the vectors is like the direction that the flags are going to move, basically. So here, adding those vectors together, we get a vector like that, which gives us a net dipole moment. So the oxygen end is slightly negative, the hydrogen end is slightly positive. Okay? So with the determining polarity, got to draw the Lewis structure, figure out the molecular geometry. And then this is the official, more scientific way. I'll show you an easier method. See if the molecule has polar bonds. If all the bonds are nonpolar, and the one I asked you to remember was carbon-hydrogen. So if you only have carbons and hydrogens, all the bonds are nonpolar, so it doesn't matter what shape or what's going on, it's a nonpolar thing, right? And then you would indicate the polar bonds with vectors. You'd add the vectors together and see if there's a net dipole moment. Yeah. Let's just skip ahead here. All that fun stuff. To my shortcut rules. Now, this shortcut does not work 100% of the time, but it probably works like 98, 99% of the time, which is pretty good. And you don't have to think about adding vectors in three-dimensional space. So there's that. Some people like that. Most people not so much. So my rule here, a molecule is nonpolar if both of these things are true. There's no lone pairs on the central atom. All the atoms bonded to that central atom are either the same element or have the same electronegativity. Why does this work? In order for a molecule to be nonpolar, it needs to be symmetrical if it has polar bonds. Those polar bonds have to be opposing each other equally in three-dimensional space. When you stick a lone pair on the central atom, that makes it lopsided automatically. If you've got polar bonds and a lone pair, the molecule's polar. If all the atoms bonded to that central atom are not the same, if one of them is different, higher in electronegativity, that's going to pull the electrons and it's going to be a polar molecule. So let's use that idea to answer this question. A molecule contains 3 identical polar bonds in a trigonal planar molecular geometry. Is the molecule polar? So let's draw it. So we've got our central atom, and we're told it's trigonal planar, and that these bonds are polar, but they're also identical. So let's use my shortcut rule. Are there any lone pairs on the central atom? No. Are the atoms bonded to the central atom the same or have the same electronegativity? If the bonds are identical, then they must be the same. So, is it polar? It is not. It is nonpolar because both the conditions are met. No lone pairs, everything's the same. Any questions? So these are slides, the book reviews vector addition. that's all nice, but just remember this. Okay, determine if CF4 is polar. The nice thing about my shortcut rules is you need a Lewis structure, but you don't actually need to know the geometry. So, CF4, well, it's going to be carbon in the middle with 4 fluorines, right? And then if we go through the whole thing and do all the lone pairs and stuff, we'll end up with this. So then we ask ourselves the 2 questions. Are there any lone pairs in the central atom? No. Are the atoms bonded to the central atom the same? Yes. So that tells me this is nonpolar. Okay? So what if we had one of these was a chlorine? Are there lone pairs on the central atom? No. Are all the atoms bonded to the central atom the same? No. This is lopsided. This is going to be polar. Yes?
Well, we have to do the vectors in 3D.
No. The three-dimensional vector addition is explaining to you in a more rigorous way how the polarity of a molecule is determined. That's something that doesn't make sense to most people, right? And so the reason I came up with my little shortcut thing is because it is important to be able to look at a chemical formula and identify whether the molecule is polar or not. But almost all the time, we can do that just with that rule. The one time that rule doesn't work, well, not the one time, but one of the times the rule doesn't work, is when you have like a square planar geometry with 2 lone pairs. So here my rules don't work, because are there lone pairs in the central atom? Yes, there are. All the atoms are the same. This is actually a nonpolar molecule because, and tug of war works here, if you think about these atoms as equally strong people pulling in opposite directions on the central atom, it's not going to move, right? Because they're opposing each other. So that's one of the exceptions, but those come up very, very rarely, okay? So look at lone pairs on the central atom, that makes it lopsided. Okay. If the atoms bonded to it have different electronegativities, and really, for the purposes of Chem 1A, if they are different elements, they have different electronegativities, okay? So polarity is important. It determines some of the physical and chemical properties of molecules, and here's an illustration of how that works. So water is a polar molecule. We just looked at that. It's got a partial negative end here and partial positive end here. And these electrical charges will attract each other just like opposite poles of magnets. Opposite magnetic poles, okay? So we have an attraction between this positive hydrogen, it's just a little bit positive, and this just a little bit negative oxygen, right? So they're gonna kind of stick together, right? So over here, these solid marbles are magnetic marbles. And you see they're all touching each other. And you can imagine, one of these days I'm gonna get some, one of those magnetic marbles, they come close to each other and they go, and they stick to each other, right? Because they're attracted to each other. And that's what water molecules do. The oil is nonpolar. Oil is carbons and hydrogens, all nonpolar bonds. There's no partial positive, partial negative end. And so these guys are not at all attracted to the water molecules. But the water molecules are very attracted to each other. And so basically what these do is they like each other so much that they're going to exclude the oil molecules. So you could think of this as being like a large clique of mean girls, right? And they're just like so into each other, nobody can get in, right? Because they're just tight with each other. The reason the oil is on the top is because it's less dense than the water. There are nonpolar substances that are more dense than water, and they would form a layer on the bottom. But you can go home and get the, if you have Italian salad dressing in your refrigerator, go and look at it. And unless it's emulsified, it's creamy, it's going to have a layer of oil on top and a layer of aqueous on the bottom. It's vinegar, and that's where a lot of the spices and stuff will be. You shake that up and set it down and watch it. You can shake it up, but as soon as you stop shaking, it starts separating, right? So I think we all know from practical experience that if you have like grease on your hand, bacon grease, grease from your bike chain, anything like that, and you go to the sink and you try to rinse it off, is it going to wash off with water? No. You can spread it around on your hands, but it's not coming off because grease and oil are nonpolar and they don't mix with water. So, soap is kind of a mediator. This is an illustration of a soap molecule. It's got this long tail of carbons and hydrogens, which is nonpolar. And this will interact with the grease or the oil. And at one end, we have a polar head with some oxygens here. And so we're going to have some partial charges here. This is polar, and this is going to interact with the water. So what will happen is the soap will break the grease into little globules. So here's our globule of grease. And the polar tails are going to be in here because they go in there real nicely. They speak the same language. And out here we have the polar head of the soap molecule. So now as the water comes from the faucet, what the water sees is something that's polar. It's like, oh, okay, come along with us, right? And so it will wash away. So the soap breaks the grease up and then disguises it as a polar substance so that the water can wash it away. Any questions?